Hey guys, so I'm Matt Ranney. I'm a staff engineer at Uber, and I work on things like scaling and architecture and that sort of thing. Let's just get right to the scale. Here are some numbers, officially shareable numbers that I wish I could share with you all the interesting numbers, but these I can. So a lot of people are surprised, I think, by sort of how quickly and how far how fast Uber has grown, how far. It's basically a global operation at this point. And particularly interesting is like how many people like work at Uber now, right? Like 4,000 employees, like holy cow. That is a lot of people, lots of engineers. This is an incredibly fast growing business. So that has caused a lot of interesting things to happen. I'm gonna get into some of the more recent outages that we've had and some stuff like that, but let me first just address the question that's on everybody's mind, which is 900 people, what do you need 900 people for? Isn't Uber some just simple app on your phone? And man, I used to think that too until I got to Uber, and what I realize now is there is an incredible amount of complexity running that is behind the scenes that we're sort of obscuring, that we're making it seem simple. We operate in all the cities around the world. They all have different rules, different laws. All the markets are different, and they're all running the same software. Furthermore, we have the driver partners can drive whenever they want. Riders want rides whenever they want. It's a very, very dynamic and complicated system that is very hard to get right. These are just some of the cities here that where we operate, and as long as we can make it seem simple, I feel like we win. I think that's success. And so it's confusing, maybe as an engineer, you think well, everything's simple. Fooled you, it's not. But so anyway, in addition to the transportation business, we're also working on a bunch of new products for new markets, like Uber Rush delivers packages, Uber Eats delivers food. So you can imagine that with as fast as the growth has been, those previous those first numbers that I showed you are all kind of growth based on the transportation business. And so you can imagine sort of as these other things kick in, that it's likely that this growth will accelerate. So this is sort of an interesting situation. So I wish I could show you the real actual growth numbers. You're just gonna have to imagine that they are all up and to the right, and maybe you can check out some of these leaked documents that may or may not be accurate. So I've been at Uber for a year, and since I've been there, the engineering team has tripled, which is just crazy. And so now we're this global business, and we're entering some very challenging markets like India and China, where the competition is very fierce. And so we're still trying to just we're growing as quickly as we can into all these places. And as you can imagine, doing good engineering at this kind of pace, it's very hard. It is a chaotic and inefficient process to try to sustain this kind of growth. But that is a challenge in front of us. And further, there's something interesting. We're not the first people to try to grow really quickly. Other internet people have tried to do this before. But I think the unique difference about Uber is that there are no free users, right? So everyone who's on the Uber platform is involved in a commercial transaction. So there's no just checking your Uber. I'm bored at the supermarket, I'm just gonna check my Uber. You've got your phone out because you want to take a trip. You're gonna spend some money, you're gonna make some money on either side of the market. This is kind of a unique sort of responsibility that we have to get right compared to many other quickly growing sort of internet businesses. But as the world gets controlled more and more by software, I feel this is something that we're all of us in this room are going to have to take a lot more seriously, which is it's really easy to sort of downplay get caught up in your computer world and making your networks go or whatever, but it's hard to really see the impact that all of your software has on people's lives, but that is changing very, very quickly. As software controls more and more of actual things that move people around and vehicles and whatever they may be, internets of things, it's up to us in this room to figure out how to do this right. And so this is a pretty big challenge because there are people, these squiggly lines are all people, and they're on the other end of the software, and they're counting on us. Like, it matters, like, whether we do a good job or a bad job. And so, I mean, man, we try our best. Like, we're really trying our best. I mean, especially, like, when I say we, I mean, like, we at Uber Engineering are trying our best. But man, sometimes even we let our users down. And it really sucks. And I wish we could do better, and that's kind of, it's kind of been my job to like help us to try and do better. So I want to talk to you a little bit about like what we're doing to kind of address that. But it's interesting because historically, Uber was, on the engineering side, was primarily focused just on scaling to survive. Because the growth is happening so quickly that reliability was a second concern to just being able to handle all the increased traffic or new requirements that were put on us. So let's talk a little bit about sort of like sort of how we got here and some of the trade-offs we made along the way. In the earliest of days, Uber made some interesting trade-off, which is no engineering. Just outsource the whole thing, and that was kind of an interesting trade-off because it was really not the hard part. The hard part was not the engineering. The hard part was figuring out all the legal rules with various black car services and trying to jumpstart this two-sided market. Engineering, for that scale, it didn't make sense. So it was all outsourced, and that ran that way for a couple of years. But then as things started to take off, then engineering was brought in-house, and so the early engineers made two main services. One was called Dispatch, and the other was called API. I think Netflix still has a huge, like half of their code is still in a thing called API. So I feel like we're in good company there. But let's talk about some of these technology choices, because I feel like it's pretty it's an interesting thing. People are like, oh, PHP, Node.js, ha ha ha. When are you going to use a real programming language or whatever? And so it's cute, but man, trade-offs are an interesting problem, because for the people who made them at that time, I feel like they were actually great. It made Uber a successful business. They made a PHP thing and that worked, and then they're making this Node.js thing, and that actually works. You can sort of make the argument that well, maybe they should have used some other thing that would have been better. And I don't know that that's true. I think it's probably the case that the trade-offs that they made then were the appropriate for the people who made them then in that time. But as we'll see, some of those trade-offs now no longer make sense, which is kind of an interesting problem. So particularly on the database side. So we use MongoDB, and it's oh, haha, MongoDB. A lot of people love to hate on MongoDB, but I mean, it worked. It was fine. We use the SQL Alchemy ORM on the Python side, which let people get started faster, but has turned out to actually be one of the single biggest things limiting our scaling, as we'll see. So we cruise along for a while. This is happening, and then MongoDB is getting kind of slow. But it turns out that Dispatch, all of its database needs are largely ephemeral data anyway. So disk drives don't even really need to be involved. So they switched that whole thing to Redis, and then that's pretty good for a while. They're chugging along, and then an interesting thing happens, which is the MySQL side that the API is talking to, it keeps breaking. Whether it's the API side or the MySQL side, it's sort of hard to say, but because I wasn't around then. But it breaks a lot, and so this is a real problem, because if Dispatch is down, Uber doesn't work. Oh yeah, I forgot to mention, on the API side, there are also all these celery queues, the Redis-backed celery queues that the Python side is talking to, and so as long as Dispatch is up, a trip can keep working. But you might not be able to log in or sign up or whatever, but you can still kind of take a trip and finish it even without API. So then the problem is that if API is ever broken, then Dispatch wants to be able to work independently. So they built this thing called the object node, or ON, which is kind of a data access layer. So it's how Dispatch talks to API. So it makes all of its requests through this thing called the ON. And the ON has a curious property that it is the one that's actually talking to all the API services and their downstream databases. But the ON has a Redis cache that it doesn't use. All it does is kind of write data to it as it passes through. But then if API is ever broken, then it will use the data that's in the Redis cache. And this sounds all crazy, and it is kind of crazy, but it's there because we couldn't figure out how to do invalidation. So remember the API side is using this complicated ORM, which, again, good idea at the time, but now we're starting to get like, we're starting to feel like the pain from this thing, because now there's no way to invalidate this awesome cache that we have, because it's just kind of all magical, and there are different ways to hook into it, and it does like lots of surprising things. So anyway, now we have this ON layer in between dispatch and API. And so, oh yeah, New Year's Eve is the busiest day of the year for Uber, and it always represents this kind of scaling milestone. So as the year sort of, if it gets toward the end of the calendar year, pretty much what most engineers are worried about is, will we make it through New Year's Eve? And so the New Year's Eve traffic is 2x what the biggest day was earlier that year. And then what we find is later, like in March or April or so, the baseline traffic is what the New Year's Eve traffic was from the few months ago. Anyway, so there's a big build up to getting to New Year's Eve, and it's always a challenge, and everyone is always very, very happy after we make it through New Year's Eve. So so this pattern starts happening where we just barely make it through a New Year's Eve, and then at the beginning of the next year we're like, man, we are never going to let that happen to us again. And so we start breaking out API, because API has become this big monolith. And so we start breaking it out into some other services. And then we think, well, our ORM's talking to MySQL. We got some Postgres expertise in-house, and we think, we could really do a lot better job if we switch this thing to Postgres. And plus, there's PostGIS, and Uber obviously does a lot of geospatial stuff, so we should switch this to Postgres. So we do. And then the New Year's rolls around, and it's a total disaster, just barely survive. And the next year, we're like, man, we're not doing that again. And then we start building new services using MySQL in a separate database. But meanwhile, there's still this one API with this one Postgres database that is actually still with us today that we're desperately trying to dismantle. So 2014, we can see that by the end of 2014, at the current rate that we're scaling, that we're just not going to make it even to the end of the year. We probably won't even make it to Halloween, let alone New Year's. This Postgres is just going to fall over and die. This one Postgres behind API. And so it's also weird too, because the actual number of transactions per second is super low, but the ORM makes it super complicated, and you accidentally make these really long running transactions, and it's really hard to debug. And so our Postgres is doing hardly any actual throughput, but it's still just totally thrashed because ORMs. Anyway, so we set about to make our MySQL sharding solution, and this is this thing called Schemaless, which is going to be open sourced soon. And it's a desperate race to finish it before the end of the year, because Postgres is going to totally melt down. And miraculously, it does finish in September. We launch this thing, and we get the trip store out of the main Postgres database. This is right around when I started, September. And so then we made it through New Year's, and this was pretty great. But there are still a number of problems, because we still have a whole bunch of stuff stacked up behind this one API, and this one API database is Postgres. We have a whole bunch of these other MySQLs, which are sort of, they've got a little more runway, but they're kind of on a similar trajectory of availability challenges. So what my first job at Uber was to re-architect the dispatch system, and so we made this new dispatch system that no one could figure out what version number it was. There was much debating, and so eventually we just said, nah, it's X.0, and that's the actual name of it now. So we have dispatch X.0, and we got rid of all the Redises, and we replaced them with this this consistent hash sharding deal that we embedded into our applications. It's an open source library called RingPop. And then we added React to the mix for reasons that I'll get into in a minute. So this, you can sort of see how we started out and life was very simple. And we chose stuff that seemed to make sense. But then as we got further along, these trade-offs had to be reevaluated. And another way of saying this that I feel like a lot of people translate this to is like this concept of technical debt. So like I find technical debt is this really interesting idea because like people use it all the time. Like, oh, you have too much technical debt. Like, oh, this sounds like technical debt. But like what actually is it? Like no one can really say like what it actually is. I mean, yes, we all agree it's bad, and maybe if you're sophisticated, you'll say, but it's necessary, just like real debt with money or whatever. But it's weird, like you talk about tech debt, but like we don't all agree what it actually is. For us, it is really like the trade-offs that we made when we were smaller now no longer make sense. So, for example, there are multiple single points of failure in the architecture. Like a single machine, many different single machines could take down the whole thing. It's pretty bad. But at the same time, like half of the engineering team has only been there 5 months. So that's also weird. So like documentation, probably not a lot of that going on, right? I mean, so like tech debt takes many forms, but I want to focus on these trade-off idea. And yeah, so anyway, the problem is, the actual like tangible result of all this is this thing just breaks. Like it breaks way too often. And these outages are incredibly painful because as I said, like for users, but like this is like people's jobs, you know what I mean? So it's like even brief outages are super painful. Even when we plan for handling failure in our designs, when these actual failures come around, like a lot of times the safety mechanisms, they don't kick in, or maybe like they never worked in the first place. So you might like a lot of people are sort of I don't know, frustrated is maybe the wrong word, but like it seems like a paradox that we've made like a bunch of these responsible choices to try to make our systems more reliable, right? Like we used very mature, proven database technology like MySQL and Postgres, and we actually like bought our own machines. You know what I mean? Like we're not using some unreliable cloud deal. Like we actually bought like real physical computers. And the stuff is actually more reliable. Like it's more reliable to like have a piece of hardware that like you own and your network that you own, and no one else is gonna randomly like do something to it because it's yours. The problem is, as the number of components in a system increases, so does the chance that any one of them is gonna be failing at any one time. And because at first they don't fail very often, like it seems sort of weird to maybe even prepare for these kinds of failures. Because like, like maybe a rare machine fails once a year, and you have just a few machines, like, it's hardly worth the engineering effort to figure this out. But like, as you get more and more of these things and they start failing more often, like eventually they'll start failing like once a month and then once a week, and now we're to the point where we have a machine fail like almost every day. And so, I mean, like let's just take it to its logical extreme. Like what if we were on AWS where you would get a brand new machine that is sometimes already broken, like it's pre-broken the moment you get it. Like this can happen, right? And so this, obviously, like AWS is a fine service. I don't mean to disparage them. Like they offer tons of features, right? Like all kinds of amazing features that would be hard to implement otherwise. And they're really clear about what you're trading off. And so like it's just that consistency is not a thing you get. Like there's no way to say like I want a system that I for sure will just like work the way like a piece of bare metal hardware will. Also, like as an aside, like this is a picture from one of our data centers. Like here's a thing that you might not realize you're trading off. Like when you go to AWS, is like look at how awesome that is. Like you can actually go to a data center and like feel hear 100,000 fans and bask in the blue LED glow or whatever. I mean, you can just go see your software like where it's running. It's pretty cool. Not a thing you realize you're trading off maybe, but if you get a chance to go to a data center, if you've never been to one, they're awesome. Anyway, to avoid all this uncertainty, we did the responsible thing and like we bought this dedicated hardware and used these traditional databases. And generally speaking, like they are pretty reliable, except this whole, this cumulative failure thing like starts to make this problem make our system not so reliable. Compounded with, now that we have all these engineers, like chances are they're not gonna like wanna build more into this monolith because it's just really hard to have this many people working on all the same, the exact same software this quickly. So we went full on microservices. We have over, well, almost 500 microservices in production right now. And also, like, man, I just hate the word microservices. It's so weird. Like, micro, like, is nanoservices next? Like, I don't know. Also, like, it's just weird. I get that words mean whatever, you know, you make them mean, and like language evolves or whatever, but I choose to stage a micro protest, and from now on I'm gonna call them services. So anyway, you know, we're not the first people to deal with this. Like Netflix has sort of already gone down this road. They're on AWS and they have a lot of services, and AWS breaks out from under them all the time. So they had to like figure out how to adapt to this, and so they built this, the Chaos Monkey to do failure testing, expanded it to do the whole sort of simian army set of different ways to exercise failure cases. So at Uber, we're building similar tools to exercise failures in our infrastructure. We have this internal release deployment tool called udeploy. A lot of tools at Uber start with U, for obvious reasons. So our failure tester is udestroy, so that's pretty cute. And I'm sure, it's weird. I feel like it can't just be like Netflix is the only one that's doing failure testing, but I feel like they're just the only ones that like open sourced it and talk about it publicly. People should like talk about this and open source however you're doing failure testing, if you're doing it. It's pretty useful. Anyway, so this is what udestroy looks like. This is on track to be open sourced soon. Lets you do like a bunch of cool stuff, like all those things. And the plan is we're gonna subject all of our production services to random udestroy sort of like annoyances all the time. Like, as part of the pre-release process, as well as just like during production. So I've been working on this for a little while, like getting failure testing adopted, and I found some interesting surprises with like mostly like kind of cultural surprises. It was kind of interesting how a lot of engineers react sort of viscerally to this idea that we're gonna like randomly kill their software. Like, I don't know if it's because they're just personally identified with this, work product or exactly what what's going on here, but people are just, they get really like, they're not so happy when like it's not a popular idea that we should just kill stuff all the time. And I think like a big reason is that like deep down, like or maybe not even deep down, like it's probably gonna not work right at first. And this might make you look bad because like you wrote software that's not like as highly available or fault tolerant as you would like. And so, I don't know. I think we have to get over that and like start make sure that like stuff survives after you kill it. But like failures are going to leak through like at first. The end result after you subject yourself to this failure testing though is you'll have a more robust system. And right, so. We crossed this hurdle, and then this brings us to the next logical step, which is databases. And so databases run on computers, and computers fail, so we should failure test databases, right? And every time I say this, like people just look at me like I'm crazy. Like you can't kill the database. Like maybe you can just wait for it, maybe it'll die, and maybe you'll have a thing waiting to take over, but like you can't intentionally kill it. Like that's really bad. And I think this is just where we have to go, though. Like, I want to kill all of our storage components, even Redises and Elasticsearches and whatever. I think it's the only way that you're going to truly know whether it's going to work. So, why do people resist failure testing of databases? I think a big reason is, I think it can become a way to visualize this is. You think about like how do your traditional SQL databases get scalability and availability? It's through replication, right? Like you get some replica of your data. Now you have two copies of your data, and then if one of them breaks, you can use the other one. And this is like the master-slave model. And also, let me just say, like, we as an industry have got to get past like invoking images of slavery all the time, like masters and slaves. Like, good one, guys. Like. If this was called like Hitlers and Jews, like there'd be a super moral outrage, but instead we're like, masters and slaves, it's fine, like no big deal. There's so many better terms than master and slave, like leader and follower, perfectly reasonable. Primary and secondary, also nice. Queen and princess, even better. And if I can't appeal to you on this naming thing as like, you know, because you think it's somehow too politically correct or whatever to like not want to invoke images of slavery, like let me try to just appeal to you as a logical thinking person, which, you know, programmers typically are. This metaphor is totally broken. Masters and slaves, like it is a terrible metaphor. Like if you're in like master-slave times where you have slave masters and the slaves are doing all the work, the slaves are doing all the work. In your master-slave replication topology, like the master is usually the busiest one and the slaves are kind of not down there, so it doesn't work there. Also, like if your master dies, your slave master dies, maybe some kind of Django-esque retribution or whatever, like what you gonna do? Are you gonna like promote one of the slaves to be the new master? Like no, of course not. Like what you're gonna do is get some other white dude to be the new slave master, and so like that metaphor is totally broken. But like, what if the queen dies? Well, geez, if the queen dies, like who is obviously going to be the new queen? Well, of course you would promote the princess to be the new queen. Like it's a much cleaner metaphor. And of course, you know, some people say like, well, geez, even queen and princess, like aren't you still sort of evoking like this kind of imagery of like British colonialism atrocities? Like, to which I say, get it together, white people. Knock it off with the atrocities. Anyway, like masters and slave, terrible idea, but also like exposes this sort of like weakness in this from an availability perspective, because you get this sort of special node, right? The leader, the queen that you have to like run all your stuff through, and if that thing dies, like it's probably going to be bad. Like it's going to be a pretty major heavyweight operation to switch over. Maybe you can get good at it, and you probably can if you practice. But you know, it's kind of like the power situation in a data center, right? Like if you don't ever test the transfer switch, like the time you have a big power outage, maybe the mice have eaten through, and like now your transfer switch doesn't work, right? So to that end, I would now like to explain how we had our worst outage ever. It is related to replication, and I want to also say that these are the facts that happened. I'm not trying to judge anything about the people who did the actual work. They are really, really good engineers that I have a lot of respect for. They did a lot of this work. I present it so that we can all learn from what actually happened. So this is text from the actual internal postmortem. It was a pretty bad one. It happened not too long ago. The API was down effectively for 16 hours. So it's like pretty bad. But luckily, remember we talked about how there's that ON layer. So the ON is basically saved us, and it made it so it was a pretty big emergency, but it wasn't like a life-ending kind of emergency. So here's how it went down. 4:10 a.m. Uber has engineering offices in Europe as well as here in the US, and so work goes on 24/7 on a lot of these things. And in preparation for going to China, we change S3 command, but it unfortunately requires new permissions, and that meant that all of the wall segments were no longer being successfully archived to S3, which meant we used up all the disk space. This is a graph of the disk space on the Postgres primary. And as you can see, it goes all the way to 0, which is too low. So you might think, wow, don't you guys like have monitoring? Like surely, like someone would have been paged. And indeed, someone was paged. And this is what the text said. It said, disk critical. You got 81 gigs left. But trouble was, engineer at the time was on it, like was ready to look at this, and looked at that and was like, oh, that's just one of those downstream replicas, and like not actually that important. There was actually what seems to this engineer at the time to be a much more important issue going on that he was working on, and he was like, yeah, I'll get to that, it's no big deal. An hour later, it goes off again, like it's getting worse, you got 36 gigs left. Again, acknowledge the alert, back to the more pressing matter, 8:11, you have 0 gigs left, and then 8:14, API master database becomes unavailable, master process crashes. So this is bad news. Good news, though, is we have a lot of copies of our data. This is what the replication tree looks like. And you can see DCA1 and Peak1, those are whole other data centers. So in those data centers are similar topologies so I mean, we have a lot of copies of this data. It's obviously very important, so we bought a lot of computers to put it on, so, you know, in case something like this happens. So no big deal. We're just gonna like promote one of these other things, and that'll just be the new primary. So, or even if we have to do that, right? Like maybe we can just fix it. So we escalate, the first engineer looks at it and is like, oh, here's your problem. Like all this old stuff is accumulated. I don't know what's going on there. Removes all the old accumulated stuff and tries to start Postgres again. And of course, this corrupts the database. So, whoops, the next step was we promoted. Now, why can't I read that? It doesn't matter. There's that one. Build me. I don't know why. It skips. Anyway, we promoted 8. So okay, no problem. Like we've lost some of our capabilities, but well, we got a lot of let's think carefully about this. Let's not make any mistakes. Let's just promote 8. We got the run book, is what the previous slide said. We read the run book and it said, here's how you promote. And so we did, but the run book had an error in it which neglected a crucial step, which is how you switch the archiving out. And so now this thing thinks it's the primary, but nobody else will be able to follow it. So we decided to bring up a couple of the followers, and seems like we're bringing things right on back. It's going to work. Now we got a topology like this, so we got a couple of downstreams. Things are pretty cool, except why am I don't know. It doesn't matter. They can't follow. The new replicas can't follow because the stuff's not getting archived to S3. So we finally figured this out. So now it's 9:30, right? So we've been down for an hour. And so we copy all the stuff up to S3 and then get the replication thing, the restoration catch-up process going again. And so this is okay, but it's taken forever. And so then, bad news. Turns out, now it's 11:43. Turns out corrupted wall segment somehow, probably with all the r-syncing and I don't know, whatever. In the chaos and confusion of this very important outage, some file somewhere gets corrupted, and so now none of the replication works right. So this is pretty bad. It has this very helpful error, invalid magic number 0. It's like, yeah, great. Okay, and so the whole thing is a total disaster at this point. But, well, look, no, don't worry. We've still got more copies. Like, it's going to be okay. We're going to make it through this because, like, look at all those things that are still white. Like, we can easily, like, restore from some of the remaining things. So, but again, it's getting late. So my slides are auto-advancing past the fun text. Let me just read what it actually says because it's super good. Our consultants suggest that we may be able to rsync the data from Postgres 8 to other followers. So we try to do this, and now Postgres 18 is out of commission. This rsync is going to take like 8 hours, and it's super bad. So now the consultants believe that they may be able to write a C program that would allow us to promote Postgres 5 in a way that would skip the corrupted wall file. This program would effectively bypass the normal safety mechanisms built into Postgres. Yikes. So we do this. And you can't read the text. I'm just going to have to read it to you. The C program allows us to issue so it's 3:20 a.m. now. So it's 3:20. Things are bad. It's been down for a while. People are writing C programs to edit, change the way the database works, and they're deploying them at 3:20 a.m. The C program allows us to issue commands to Postgres 1. We are able to promote it, but Postgres 5 is unable to follow the promotion. So now, we thought we had, the solid red one is the new primary, but No dice on that one either, so we give up on 1 and decide to promote 6, which is immediately successful, but getting follows from replicating from it is taking too long to recover by S3. So we have this Ceph thing, and we just reroute it all so like it's going through our local Ceph, and this is sort of better. And so now it's 7 a.m. It's like 11 hours later. We've been down, the whole night. Engineers have been up all night. This is really, really bad. We reparent, which wings us 5 followers. So now, like, hooray, like we sort of have our thing working, sort of, but the system will not work with this many replicas. Like it needs, I forget how many it needs, but more than 5. So we attempt to reparent peak 1 to Postgres 6. This does not work, and peak 1 is left unrecoverable. Sorry, peak 1. That whole data center is now no longer usable. We still have DCA1. Fingers crossed, if we can make this work, we might just be able to bring the site back online. 9 a.m., we are successfully able to reparent DCA. So we get DCA1. We get these guys. We reconfigure the whole deal to like serve some portion of the reads out of the other data center. And then May 14, 10 a.m., a whole extra day later. So like it's basically a two-day outage for read capacity. Then all systems return to normal. So what did we learn from this whole arduous process? Some interesting things for our own operations, but like I feel like I've run into this problem enough times that like it's worth maybe repeating to a larger audience. Like the subtleties in the alert text can be incredibly valuable. So if that engineer had gotten an alert that said the Postgres primary is running out of disk space, he would have been like, oh no, total disaster. Like nothing is more important than this. But instead it was like blah, blah, blah. One of those 18 Postgres machines or something is like sort of running out of disk. It's just the one. Probably fine, right? Except like if they had just included one extra word in that line that said primary, it would have been a totally different deal. Because we had like 3 hours, right? Like during those 3 hours, we probably could have figured it out. Second thing is threshold alerts nowhere near as useful as derivatives. If we were alerting on the rate of change of the storage, 4:10 a.m. Right after that thing landed, like half hour later, alerts would have been going off. People would have fixed it immediately if we had been alerting on derivatives. And this was like really enlightening. I mean, none of our alerts were really on derivatives. They were all just on various thresholds that all seemed responsible. But yeah, derivative alerts are the way to go. Maybe a thing you could do with one of these fancy monitoring systems that people are talking about out there. Also, man, make a lot of copies of your data. Like if we didn't make so many copies of our data, this would have been super bad because we were just running around, just breaking stuff, trying to get it all working. Like the fact that we had all of that extra capacity made it possible to get through this. And of course, practice these failure scenarios. Like we had a run book, but it was not exercised very regularly. And then we had a lot of really smart database people who could work on these problems, but like this particular kind of thing is something that they just didn't practice very often. So, like what is this, in this broader context of like, sort of failure testing, like is there some better way that we could have designed, a better way to get, databases working in our environment? Like, I think so, because I feel like this replication pairs kind of idea, it's sort of like not having an abdominal wall and your guts are just like hanging out in your hands, because like in case it's like the replication technology, the mechanisms for it are just like sitting right out there. Like you can just change them and change S3 command and just change all this stuff. Like, and it's neat if you want to, do surgery on it. Like it's cool that it's all just sitting out there, but like I would actually rather have an abdominal wall that like, keeps all my intestines intact. I mean, it's like, people when like cars got rid of carburetors, like people said, oh, I can't work on them anymore. Like that's true, but I think most people would just rather have a more reliable car. And I think we can get there. Like we don't actually need technology that is tailored toward being able to be fixed. We can build stuff that just like works better and doesn't need to be fixed. So like, I'm obviously not the first person to think of this. Like Amazon sort of realized this a long time ago when they published this Dynamo paper. My favorite part is right in the intro where it says, even the slightest outage has significant financial consequences and impacts customer trust. So the way that these things work is there is no special node. The requests are serviced by multiple nodes, and just it does extra work all the time. And this is kind of the way you'll find like a Cassandra or a React work. And it's a really good model. It's a model of a database where you can subject it to failure testing in production, and users will not notice. Now, there are, of course, a lot of caveats about making sure you have extra capacity so when it does fail, and maybe you can't kill, maybe not as aggressively as you might with software that like restarts really quickly. Like these are pretty big, the Java runtime and the Erlang runtime, pretty big pieces of, pretty big moving parts that like rapidly restarting them, probably not a great idea, but like you can, and we do failure testing on these databases, and it's pretty good. I think it's a better model than replication pairs. But would React or Cassandra have prevented this worst outage ever? I don't know, maybe. Running out of disk space is a really tricky problem. It may have been that all machines ran out of disk space simultaneously. That would have been like super bad. But I think the difference is that the replication stuff is all kind of like what these things do. It's not like up to you. You're not like rooting around in the guts of the replication to just tailor it to your environment. Like you just get a modern car that like works better. It's not up to you to be an automotive engineer just because you want to drive somewhere. So here's the thing, like these systems, maybe they fix some of the problems, but they have another curious property about them that these React and Cassandra style things that has actually caused other outages for us. We'll see if my text shows up. Does it? Hey, all right. So this is actually an outage that happened very recently with a React cluster. Like people noticed it was pretty bad because it was a dispatch outage. So it actually took out dispatch briefly. And here's how it worked. So we have this 10-node cluster. It's just sort of managing this like ephemeral state for the dispatch process. And due to an as-yet undiagnosed network problem, that basically this React cluster was exercising because it was kind of like the busiest network talker in this part of the data center. And there was this weird thing where some of the TCP flows would experience intermittent multi-second pauses, which sounds like, wow, that must have just been like setting off alarms all over the place. Like surely you would have seen this coming. When this happens, React tries to helpfully decides that node's probably overloaded, and it should help out by spinning up a fallback vnode. And unfortunately, due to a misconfiguration on our part, when it does that, it creates some sibling values. So this is mostly our fault, but interestingly, React increased. Oh, yeah, I did say that on this previous slide. React. These delays are masked by React, right? So none of our graphs were going off and saying like, hey, there are these weird multi-second latencies. In fact, the performance was awesome. Like it was super, super fast. Like everybody was happy with how React was working, except deep inside of React was deeply concerned with how things were working because of these multi-second pauses. But because multiple nodes are involved in every operation, this delay was masked. And so we had this like problem that was just about to be a total catastrophe, and we were completely blind to it. So the delays increase, and React is no longer able to mask this latency. And the clients, the service in this case, they respond to this increase of latency because they can't get their work done fast enough by opening more connections. This, of course, makes the problem worse. And if the problem is your network is too slow, it turns out actually that it's the number of connections that's causing this thing, causing these random pauses. And so now we just made the problem super bad. So now the additional connections, sibling management and client retries, blow up the file descriptors on all of these machines. I think it was something like, I forget what we had it set to, but it was a tremendous number of file descriptors were all consumed for this problem. And then to make matters worse, like bad timeout handling and all sorts of weird other problems, cascades all the way to the edge. Dispatch is completely off. So this is super bad. So 3:47 p.m. Luckily, and again, we have crazy auto-advancing behavior. Anyway, so like 15 minutes later, we luckily still had the dispatch not X.0 thing was still kind of like hanging out in parallel because some cities still hadn't been migrated off of it. So we were luckily able to just flip the world back to this legacy system and got the business working again. So this was incredibly painful. Because unlike that, so the impact with that Postgres outage was basically people couldn't sign up. If you're already a customer, like the ON cache and all that stuff, it would kind of like work out. You would take a trip, it would just land in some queue somewhere. But if you went to sign up, sign up would work, but it would just wait in a queue. And then when you would go to like actually take a trip, we wouldn't know who you were. You wouldn't be able to log in. So basically, signups were down for like a day, and that's bad, but not as bad as like stranding people. So. Here's the thing, like this dispatch has to work, right? Like if it does not work, we are totally down. Failure testing was something that we were doing, and it's cool, but what we needed to have done was delay testing. If we had simulated the delay of just the clients talking to React, we would have found out that like the clients were configured incorrectly so that they would just do the exact opposite of what they needed. Instead of like shedding load, they amplified the load. So delay testing, it can sort of expose some of these latent issues. Also, man, proper back pressure is super, super hard, especially like in a big service-oriented architecture where you got all these different implementations doing various different things. It is a really tricky problem. Also, it turns out, depending on how you looked at some of the stats that were coming out of React, we actually probably could have known that something was not right. Even when you see what those metrics are called, like, it doesn't seem like anything you should be concerned about, but these systems like Cassandra 2, like there's so many different metrics that you can pull out of them, and understanding what they actually mean is incredibly important. So we have problems like that, only we have them like with our databases. We also have them like with all of our services too, right? So this cumulative failure like gets even worse with microservices. Oops, I said it. So we fixed, our attempt to fix this is we wrote our own RPC protocol, this whole RPC framework we call T-channel. And we made a service discovery and routing system that uses this thing. Anyway, it's open source. That's the point of the slide. You can check that out. So this the reason for doing such a crazy thing like this is that, remember in the history slide, you could see that like basically most of Uber is Node.js and Python. And when you look around at sort of mature RPC frameworks like Finagle or something like this, it's basically all like JVM. And like if you want like a good experience, like be on the JVM. And like JVM is like not a thing we're on. And so we wanted something that had, where Node and Python were first-class citizens. Much of Uber is now moving to Go, and so like we have this cross-language problem. And using HTTP and JSON, which is our RPC protocol, from when we started, was actually a pretty good trade-off, I think, for when we started. But with this many engineers working on this many services, like it's just crazy. HTTP implementations, like they're all different in like weird, silly ways between these different language runtimes. JSON has all kinds of weird problems about like, yes, as a human being, you might be able to look at it, but it's like super slow, and it is really hard to validate in some sort of cross-language way. And so we wanted to get something that was consistent, gave us a consistent interface to make RPCs in all of our runtimes. And so that is what we built. And that is, that sort of topic is kind of a whole other thing. So I'll just leave it at that. Like if you want to know more about that, you can check out the how all that stuff works. You can check out the GitHub, or you can ask me later. So the problem, like with all of this like magical setup, right? Like we've got this super cool RPC framework, and we've got this discovery and routing deal, and we got these distributed databases, and like now everything is running everywhere. And now the problem, of course, the reason that any of this is bad is latency. So the overall latency before you can respond to your client, it's the same as the latency of your slowest component. And so like the way this works out is, let's say you have your service, and generally like you're pretty good, right? You can respond in 1 millisecond, but your P99 is 1 second. So that's kind of a bummer, but like, oh well, it's only 1% of the time. But as soon as you get into sort of an RPC fan-out type situation, then the chances that you will hit that slow case actually increase substantially. So like, this becomes a real problem that like the thing is just maybe is more reliable, but it's like slower. And this kicks in really fast if you're on the P95. And even on the P99.9, like still with big fan out, like you fall into this slow case like pretty easily. The way that we've chosen to handle this is taken from this Google presentation that you should totally check out because it's awesome. But there's this cool idea in there called backup requests with cross-server cancellation. And the way it works is, say you have a service B and it's got 2 equivalent instances, B1 and B2. You send a request to B1 and you say, by the way, I also am going to send this to B2. And then 5 milliseconds later, or some time offset later, you send it to B2 and you say, by the way, I also send this to B1. And then when they start to work on it, they cancel it. They cancel each other. So in the common case, the work only gets done once. But if B1 or B2 dies or is too slow, takes some GC pause or whatever bad thing happens to your service instances, like your end users don't notice. So you'll note that this is kind of similar to the Dynamo model of just like doing your work on multiple things instead of just on the one thing. Anyway, if you're curious, T-channel that's one of the design goals with the T-channel and Hyperbond was that we could support this model. Also kind of a challenge in a lot of other things. Another interesting problem is like, what if your whole data center fails? We have a lot of this ephemeral data, and when you add it all together and you try to replicate it, all these like location points, it gets really expensive to replicate this data everywhere. So what we do is we actually use the partner phone as sort of a failover device where like, if so as the trip is making progress, it sends up to the server, and the server sends back an encrypted state digest of the trip so far. And then if we ever have to do a failover, the partner app tries to make progress on the other data center. The other data center is like, I've never heard of this trip. Well, hang on a second. Let me, tell me what you know about it, and then we'll make progress. Of course, the other data center has the key and can sort of decrypt it, and the trip continues without having to sort of replicate this constantly to every data center, which would just sort of unworkable for us. Anyway, the good news, if you take all this stuff and put it together, we can get to a model, and we're definitely not there yet, but this is where we are trying to head, where we can make everything crash only, where we don't have to do a graceful shutdown and like let things drain and sort of tenderly and lovingly caress our services into like, for upgrades or whatever. Like we can just kill them and let new ones take their place, the work gets rerouted, and exercise our failure cases as part of the release process. Or just whatever you want to do, just always be able to kill stuff. I think this is where we want to get. So once you can get to this point, you can be more insulated from these kind of systems failures. But really, like I think you're also more insulated from human failures as well. If you have a system where you can just kill it whenever you like just Google around for like how many outages are caused by people just like typing the wrong things. Like basically all of them. So, I feel like this is, this is sort of where we need to get to, both where we as a company need to get to, but like we as an industry need to get to. We've got a lot, like we've been able to get away with a lot of sort of, I don't know, not so reliable stuff in kind of like early internet stuff because it was like websites or whatever, you know what I mean? Like who cares, fail whales, oh, cute. But like where we're headed, where our industry is headed, that is no longer going to be acceptable. So I think we need to up our game with failure testing and sort of like really rigorous fault tolerance. It wouldn't be able to mention databases without Brewer's conjecture, also the CAP theorem. I feel like engineers resist failure testing also because they intuitively think CP is like what you should get. But I submit to you that the world is an AP world, and people are happier if you give them a system that is up more and occasionally wrong than if the system is less available. So Yeah, that's it. Thanks.